if you joined us at Andy's talk, that was a really great talk. One housekeeping note, the gala is sold out at the moment, but we do have a waiting list. So if you're still interested in purchasing a gala ticket, please go to the reg desk to be on the gala. And now to our first afternoon keynote. Jason Kursan is the Director of Advanced Exploration Systems Division with the Human Exploration and Operations Mission Directorate at NASA. Among his previous positions in NASA, he has been the Chief Technologist for Space Operations. He holds a bachelor's degree in electrical engineering and physics, and a master's in computer information systems, and is currently a PhD candidate in engineering management at George Washington University. He is married and has 2 children. Please join me in welcoming Jason Kursan.
Thank you, guys. I'm going to walk through a few different things. I mean, the title of the keynote was this pioneering space. And one of the key principles and shifts of the way we've been thinking about exploration. In the past, we've always thought about exploration, human exploration, as very kind of large, monolithic programs. It was that way for Apollo, it was that way for when Constellation was formulated and such, but we're really striving to figure out how to think about exploration, not just about the singular task of flags and footprints, but rather how do you expand into the solar system in a systematic way that's sustainable and can actually bring along even the private sector in those endeavors at the same time. If I can have my chart deck up, I'll walk through this. Okay, so one of the key principles of this is we've been looking at you've seen this chart all over the place. Everybody at NASA has been using it lately. But there's a real key element in here. And one of the phases that we're in, you could actually talk about our phase in low Earth orbit as Earth reliant, meaning that we have a robust supply chain, we have easy access to change out parts, sustainability from a technical standpoint of hardware and stuff, you can do replenishment. If you have an issue with a crew, you can quickly return to Earth and be in a hospital in very short order if you have an emergency. The far right-hand side of this, the Mars ready, or you could also think about this as space reliant or Earth independent. On that far right is how do we figure out how to live for long durations off of the planet in a way with high reliability hardware and the such with very limited or no abort scenarios. And figure out how to live off of the planet for an extended amount of time. But if you look at those 2 extremes of where we're at today in low Earth orbit and where we need to go, that's a pretty big step. So what we've been talking about is where do we spend the time and what activities do we need to do to advance the capabilities to get from point A to B from a capability standpoint, and that's this proving ground piece. And we talked about where better to do some of the proving ground and advancement, but still where you're relatively close to home and you can get back and repair things or replenish things in a short order of time. So talking about activities in the cislunar space about that. One of the other things that we've outlined for us are anytime you're laying out kind of a pioneering or what are you going to be doing is it's important to keep some principles to help guide you along the way. These principles, we've been evolving them, so if you've seen them in the past, you may see a different version up here than we've shown in the past. But we had 6 of them here. The first one is living within our means or living within our current budget that we have. In the near term, we do believe we have enough funding at NASA to execute what we need, but over the long term, we do need to increase commensurate to inflation. The past several years, we've been operating on a fixed budget, and that's not sustainable in the long term, as many of you guys know. The other piece is technology readiness or capability readiness. We want to be able to have a mixture of technology that we're applying, both the high TRL technology in the very near term, but keeping a portfolio to ensure that we're getting the next generation solutions we need to send humans further and further. The next thing is cadence. It has to deal with near-term mission opportunities. One of the aspects of space and keeping stakeholders and the public engaged is a constant cadence of missions and having flight on a regular basis. This also drives us about thoughts about let's not have a long period of time where we have no human spaceflight activities or no flight activities going on, where it requires large buildups of systems just to do a singular mission. So if those that have been following Mars planning for the decades, we had our DRA, Design Reference Architecture 5.0. It required the building of a large number of systems, and then magically we'd have 9 to 12 heavy lift launch vehicles all launching within an 18-month window, and they'd all go well, and you'd assemble and you'd go off to Mars. For many reasons, that's not a realistic approach. So how do you get a constant cadence? Do you do pre-emplacement and those types of options that you have out there? The next piece you're all aware of in this room, commercial business. So how do we start baking in from the very beginning commercial opportunities? With station in low Earth orbit, quite frankly, it really came after post-assembly. Then we thought about how do we do commercial resupply with cargo and now with crew. But if we think about exploration, how do we start designing an architecture that allows for that commercial expansion and where markets are to be baked into the architecture that we have from the get-go? With that, we also have the multi-use infrastructure. The other piece that's core to us is we need to stop throwing away hardware. So we today have 30, 40-year structures for habitats that are operating in low Earth orbit. So we can build long-duration spacecraft and habitat systems that will last us decades and potentially could be multi-use or allow us to use for a whole series of missions or multi-decade campaigns. So this is key to this is minimizing the throwaway of every piece of hardware we put into orbit. And at the very end, obviously we're not going to do this completely by ourselves. So how do we work with our international partners? They have slightly different desires in some of their aspirations they have, but they can be synergistic, and how do we work together with them very closely? So we talk about this internally and externally as instead of a design reference architecture like 5.0 was and those kind of things, we now talk about things in a terminology we call our evolvable Mars campaign. What it means is there are many pathways or architecture solutions on getting us to the surface of Mars in the time frames that we're trying to do that. And one of the things we want to be able to do is analyze all of our near-term decisions to ensure that we're making the best decision today that then can carry forward all the way to the surface of Mars. Some of that activity will be in the proving ground. Some of it's related to even our asteroid redirect mission. If you look at commonality of the systems there, of solar electric propulsion and such, can that be used for cargo pre-emplacement for Mars cargo or Mars moons resupply? And you could actually place your habitats and your landers in Mars orbit ahead of time. But then you have to back that out. So how do we size the SEP system, the solar electric propulsion system for ARM, that's then compatible all the way through the architecture? So we're going through a whole series of trade space analysis. I'm revisiting a lot of our old assumptions that we had. SEP is one of the major ones. The other one that you guys will find interesting is also ISRU. No Mars mission will be done without ISRU. It's going to be critical. At the very minimum, we need it for the oxidizer for the return trip home. But we're also analyzing ISRU as many parts of the architecture. How could that be influenced even in the near-term missions? Those of you guys at lunch and heard Andy's talk, there are commercial entities, and we have a panel after this talking about some of those folks that are endeavored to go back commercially to the surface of the moon. If and when they are successful, will propellants and consumables be available to us that would then fundamentally change our architecture and be able to supply the raw rocket material or the oxygen and water that we need for our crews. So we're now thinking about how does ISRU fold in, not just for the oxidizer for the return trip, but along the way and kind of living off the land in the true style for that. We're also looking at robotic precursors. When do we send things to Mars? What sequence do we send them? In the past, we've looked at large-scale monolithic, like 40 metric ton landers. The leap of entry, descent, landing technology from where we're at today to 40 metric ton landers is pretty large. Could we break that up into smaller chunks, 15 metric tons, say, and do pre-emplacement? And some of that pre-emplacement could be the ISRU plant that we need on the surface. So we're analyzing a lot of these trades. We're actually going to be publishing updates over the next year about how we're going through some of this trade analysis to help make some of our near-term decisions, and then we'll continue to trades. One of the key difference in what we're doing with the Evolvable Mars campaign is we are not deciding every flight step from here to Mars. We are using good analysis to make us make the decisions here in the near term that are the most prudent for evolvability and extensibility towards Mars, but leaving the trade space open as new technical capabilities come online or new commercial market opportunities or utilization of commercial markets come online that we could utilize along the way as well. So it's not a laid out plan from here to there, and that makes people a little uncomfortable. However, what we need to be able to do is do that detailed design that we have to make the good near-term decisions, but then continuously progress on our step towards Mars. A couple other trade studies we have going on. We're also looking at split habitats, where you may have more than one habitat, where you're sending it in more than one piece. Could you have those on cargo pre-deployments? We are looking at Phobos and Deimos type opportunities. Is the staging point at the Mars moons one of the right opportunities for us to take a look at? And does it help with overall EDL, entry, descent, and landing, and our architecture for our missions that we have? And I referenced that we really need the commercial sector to help us, and a lot of entities to give us inputs on this. One of the things that we've been starting up in the upfront piece, a lot of the little bullets on here that you see may be familiar with you, but if you look at routine transportation, research, and exploration, and the Venn diagram, and this is overly simplifying some of this, but if you look at the intersection of routine transportation and research, you have our commercial cargo resupply going for station, and as we're going to the follow-on cargo contracts and commercial crew, those things are established, and we're obviously getting those in an operational state, and we'll be doing selections and such related to crew here very soon. We also are then trying to build the market of low Earth orbit to make that sustainable. If the space station is the destination for cargo and crew, and all it is a NASA-funded effort, it will not be sustainable. So how do we advance the knowledge gained in low Earth orbit to a point that people want to go there that are not government funded to advance the research? So how do we build that low Earth orbit marketplace? And CASIS and many other companies like Nanorax and such are actually helping us build that case for a low Earth orbit marketplace. In addition to that, now we're starting to look for exploration. As I said, instead of backing into these commercial solutions for some of our needs and requirements we have, how can we start looking at that as part of our architecture planning process up front? So you'll see that we've put out a lot more RFIs lately and solicitations than NASA has traditionally done in the past. And that may be semi-confusing to folks, but it actually is an effort to have a dialogue in the way that we can with the government side and our restrictions and try to figure out what are the best ways. So we have the evolving ISS RFI that was out there. We're asking for inputs of how do we evolve that low Earth orbit marketplace of ISS, and what are the right evolutionary steps, and asking for inputs. And thank you for those that did give us some feedback on that. We had collaborations for commercial space capabilities. Again, this is another potential out there where we share our in-house expertise on a no-cost basis to multiple commercial entities to help accelerate whether pieces they may have in their transportation or in-space technical capabilities they're trying to advance. We just announced recently our asteroid redirect mission BAA, and in that we did multiple awards to look at commercial involvement in the asteroid aspects of when we visit it, what would we do robotically ahead of time or versus what would we do with the crew there. And we have ongoing awards that will actually study that, not by NASA studying it, but by commercial companies actually telling us and doing the studying themselves. We'll also spend a bit of time on the panel right after this related to lunar catalyst. In short there, we saw an emerging market or emerging capability starting to grow in the commercial sector. We said, well, how can we help enable that with some of our excess capacity that we have and knowledge that we have, and hopefully drive even more success in that area. Now, what are the pure exploration pieces? We also have been looking at how do we advance these concepts both from an acquisition standpoint or partnership standpoint for exploration. So we've contemplated things like another BAA related to habitat technologies or habitat advancement. Are there different ways for us to work together with the private sector in those endeavors as well? So look for something like that in the coming future here as well. I would consider one of the fun jobs at NASA myself. I have a small little division called Advanced Exploration Systems within Human Spaceflight group, and our group kind of gets to do all the lean hardware development that's not the rocket or Orion, and we do a lot of that in-house. Now, when I took over and we founded AES, I was really nervous about the level of in-house work that it was actually taking on and only being in-house. So my personal druthers on that is to then reach out through other mechanisms via SBIR, public-private partnerships, in order to enlarge the trade space and involve others outside of the agency to ensure that we're getting the best ideas being brought to the table. So AES does a whole series of public-private partnerships, and I'll actually highlight some of those that we're doing today. We break down our work into what we call like domain areas or discipline areas. They're pretty logical to anybody that's worked in this area in the past, from deep space habitation to vehicle systems to crew mobility and robotic precursors. And you'll see various images of some of the EVA work that we've been doing, to Morpheus and Mighty Eagle, our lander test beds, to concepts like our 6U CubeSats as new NEA scouts to go off to near-Earth asteroids, and/or we have another 6U CubeSat with a solar cell that's also going to be looking at lunar volatile analysis as well. So a couple key things here. So SBIR. So to put it in perspective, in our R&D world related to human spaceflight, AES, which is the division I have, we have about $150 million a year nominally. The president's budget was $183. We spend about over half of that on workforce. It means that we don't have a whole lot of procurement. However, SBIR is a very productive partnership avenue for us to be able to nearly double the amount of R&D money we have going into human exploration. And we actively use SBIR quite a bit. And I know a number of you guys are contractors and partners with us with our SBIR awards that we try to drive there. We've been trying to really even amp up the SBIR involvement even higher by actually reducing over the past couple of years the number of subtopics in order to actually increase the number of awards in certain areas, so we get an increased number of trade ideas actually making it through phase 1s and phase 2s that we can bring to bear on the requirements we have. This is not from AES. This is a water production service contract that was conducted under space operations with the station. But what I leave this up here is we also think NewSpace and commercial isn't just acquiring services, but it's also how do we use commercial methodologies to do our procurements and buy things that we actually need that don't have another commercial market, but you can use the same drivers in order to get the performance you want without having to do overbearing insight and oversight on performers. This is a water production service that's been operating on the space station for 5 years. It was built by Hamilton Sundstrand. We actually procured it as a fixed price service contract. So we actually don't own the hardware that's up there. We delivered it up there and they operated it as a service for us over the 5-year life. And it worked as advertised, and it actually has the lowest down rate of any environmental life support hardware that we have on board the station. And it was procured in a very commercial way, meaning that the day that we launched it and we installed it, the day that we turned it on, Hamilton Sundstrand was actually 100% at risk. If it didn't work the day it turned on, we got all of our money back. That motivated them. And we actually removed all of our insight and oversight off of them besides safety. And we didn't have any technical insight. There was no PDRs, there's no CDRs. We didn't even visit their plant during assembly or anything. We got the piece of hardware and we got through the normal safety reviews on it, but that was it. But we acquired that in a fashion that motivated the performer, in this case Hamilton, to be able to do the right engineering, and they didn't need a lot of insight and oversight from us, and then perform for us as a service over the 5-year life that we had. I think we should be using these type of models even more, and we are branching into acquiring more of our capabilities as kind of in this methodology where we can back off our insight and oversight, but then put more control back into the community at large. Now on the other side of this, EVA suits. So we've been advancing a lot of suit technology, both internally and externally. This is more of a brag picture because the center there is a portable life support system, the PLIS, the backpack for an EVA suit. That happens to be the first PLIS built in 30 years in the space industry for human spaceflight. And it was built in record time with a large number of SBIR performers and some of our larger primes supplying components and such, but the overall systems engineering and integrated systems integration occurred on the NASA side and allowed us to go very rapidly in our design work that we had. And what you're seeing there is a suit simulator on the left-hand side, and we're actually in full metabolic load testing on that life support system. But then it allowed us to pivot very quickly. When we started thinking about the asteroid mission, we needed a very lightweight suit. So what better way to do that but using some existing potential hardware that we had. And so we took the orange ascent descent suits that we had and we actually put the PLIS on it. And we've been actually testing that modified ascent descent suit now in the Neutral Buoyancy Lab as a proof of concept that we can have a lighter weight EVA suit. And I know there's a large number of other firms out there that are also could solve some of the garment issues and even give us even better next generation than even that modified ACES suit that we have. So before we go to flight, we'll look at a lot of options on the garment side, but really advancing the life support piece as well. Another thing that you may have seen us testing is the Morpheus vertical test bed that we have. We were doing this primarily to actually regain our in-house landing expertise that we had lost over the past couple of decades, and actually figure out how to do a really lean development project with very little bureaucracy and administrative oversight on it. And what you saw here is a culmination on Free Flight 14, the one that we did at night. That was the end of a 14-flight series, a free flight series that we've been conducting at Kennedy, and we were testing next generation advanced hazard and hazard avoidance systems and such on that vehicle. But what this allowed us to do is build a lot of in-house knowledge now that we are planning to then parlay into our partnerships that we're doing under Catalyst, and I'll save the Catalyst discussion until the panel. But it really made us really smart buyers and build up a lot of expertise that we know how these vehicles come together. So now when we're working with our partners, we have resources and technical expertise to bring to the table as well. This is the short video of the Free Flight 13, which was the flight before the last one. The night video is a little hard to watch in a conference, but this gives you an aspect of what we ended up with towards the end of last year. One of the other things is you notice where we're flying at. We're flying at the end of the runway at Kennedy Space Center, the Space Shuttle landing facility runway. The other piece about this is, can you imagine 3 years ago, Kennedy Space Center allowing us to use an experimental rocket at the end of the Space Shuttle landing facility, and what bureaucracy would have taken to get that kind of testing approved. But what this is now showing is we can now use some of that NASA infrastructure that we have to work with our own and with the commercial sector in a very lean way and learn how to get back to testing hardware and manage those types of risks on our facilities and actually be able to facilitate some of that. And you saw Andy's talk at lunch, if you saw that. I mean, this is the kind of flight experiments and testing that we'd like to see conducted at Kennedy over time, of us and them working together, both commercially and NASA as well. And I'll cut it shorter here a little bit. So that allowed us, along with Mighty Eagle, allowed us the expertise to kick off Catalyst, and I'll talk about why we did Catalyst here in the panel. These are the three companies, Astrobotics, Maston, and Moon Express, that we selected there. And we are in the final throes of agreement negotiation. And and working through all the milestones collectively between us and our partners. Another aspect is we're also thinking about how do we blend long-term exploration needs with low Earth orbit commercial opportunities. So I'm showing Made in Space down the street here, and I think they were around in the booth as well. I saw them. This is the first 3D printer that will be going to the space station later, very soon actually. But what's unique about it is it was acquired through a normal contract for advancing our own needs and understanding 3D and additive manufacture for in space. But at the same time, we're setting it up so that they can actually open up a new commercial market in low Earth orbit. So we're advancing our needs, and we know we want to be able to do additive manufacturing and 3D printing on our way to Mars for repair and fixing and those types of things. But we can do that in a way that in order to open up a LEO market or enable the opportunity for them to open up the LEO market in a much more integrated way and working hand in hand with them. Another aspect of that we're doing is working with Bigelow on a demo of inflatable structure and habitat on board the space station. Happy to say that they are on track for delivering the hardware actually in January of next year for us. That is 24 months from initial signature to hardware delivery for a flight. Us and Bigelow working together hand in hand. We have a very small NASA team, materials experts and structures experts working with Bigelow and as we go through this. Our test objectives for our own purpose are actually looking at soft good structures versus rigid from a thermal performance and radiation performance. But this also now has an inflatable structure going all the way through and passing NASA safety processes to get to the point where we can actually have crew ingress and outfit the module on orbit. So this is another example of working hand in hand with the private sector. I heard a lot about CubeSats. 5 years ago, I think it is, we started our CubeSat launch initiative. And I had a lot of strange looks back then. I was in space ops and they said, why does the Human Spaceflight Division want to champion opening up the CubeSat launch business? And quite frankly, we didn't really know why. We just thought it was a good idea. And the students were building really, really great hardware. Jordy is somewhere here, and Bob Twiggs had come up with a great idea. And we didn't have a way to get them to orbit on a regular basis in the U.S. So we thought about actually breaking down the barriers to getting access to launch. Now we do a call every year, and we've built quite a bit of backlog on trying to get all those satellites to launch. But what's happened is we're no longer the main player in the CubeSat world. Now you're seeing commercial industry in an order of a year or two eclipsing everything we had done at this point. And that's great. For us, that's just an amazing explosion of markets and I think new uses and applications that you have there. And you get really neat deployment pictures off the space station and such too that everybody is just in awe of as we're deploying more and more off of the station. The other piece, one of the other aspects that as we're working with not just companies, but how do we engage citizens and the public at large? We have a very active open innovation program. Jen Gestetic probably talked about it at her panel on prizes and such. And NASA's been very invigorated with this. Again, with this, we are trying to figure out how to use prizes and challenges and this kind of distributed innovation, not just as stunts, don't write me just the latest app to show me a picture from the space station, but rather, how do I use challenges to write a new protocol? Delay tolerant, destructive tolerant networking protocols. How do I actually write all the core code that we need for that networking protocol to work for deep space? And we've been running a whole series of challenges in this area for delay tolerant networking and finding huge success in actually getting the protocol developed in a much faster and much more accelerated way of working with us and individuals from across the globe and writing that code that we have. Bottom line is, I believe we're starting to finally shift NASA into thinking, how do we work together from the get-go, and how do we actually reshape the way we do exploration planning, and starting to, from the very beginning of doing this together, not just to go out and plant flags and footprints, but really in the true tradition of this pioneering space and getting there, and trying to work actively with you. I know we could do better. and we will continue to do better. And I'm really excited to see how the collaboration between industry and NASA and academia and everybody working together actually allows us to get to Mars in a much more sustainable way, and that we can all then not have to abandon, and we keep on into the settlement of space. So that's the main driver. I don't know if I have any time for questions, but I probably can take one or two, I think, and then we'll have to flip over to the panel if there are any. Yes, down here.
Regarding Mars, in the old days, I hate to go back to the old days, but we went to the moon in a very logical, set of steps. Mercury, Gemini, Apollo. It's not clear to us that we're getting to Mars in any kind of logical way. And it's not clear to me that a asteroid redirect mission is a logical stepping stone to Mars. Can you talk about the logical stepping stones that you see to get us to Mars eventually?
Yeah, okay.
And also one more,
yeah.
As a taxpayer, how do we get our hands on your current design reference missions that I know you guys are working on?
Yeah, so I'll answer that one first. As we actually start putting all this analysis together for the Evolvable Mars campaign, we will be publishing those, but it'll be later at this year. In the past, we've always published our design reference architectures and missions like we did with DRA 5.0, and we'll do the same as we get them out there as we complete the analysis. But going back to your question on Apollo and a nice orderly sequence of events, I would challenge that statement a little bit, in that our view of Apollo is in hindsight. And when we look back, it looked like a nice orderly step of events occurring in a certain specific order. But if you look at what actually occurred, there was a lot of other planned tests, there were a lot of other planned activities, and a lot of times those just didn't get done, and there was a lot of deviation. For what we're trying to analyze here for Evolvable Mars campaign and the asteroid mission and how those components come together, if you boil down to your mission segments into in-space and surface activities, you can actually design or come up with all the capabilities and the design framework that you need for those capabilities, and not really care about the order or sequence, but rather what does the performance of that capability need to be in order to have a mission capture or a flight envelope that you have. So what we're doing is, if you take a look at EVA or life support systems, we are increasing the capability of life supports while decreasing the supply chain, and we're advancing that over a steady sequence of events. And we're going to do that for each one of the capabilities that you need to land on Mars. And so we're analyzing all the different trade space that works. Specifically with the ARM mission, there are a number of elements that contribute directly to those capabilities. One of them is solar electric propulsion, and in the past, we've mainly looked at chemical propulsion and nuclear propulsion as the entire solution, and we looked at monolithic structures and it all going together. One of the advantages of CEP is we can now send maybe smaller chunks, but we can send chunks along the way and actually do assembly of that or aggregation of that in the Mars orbit instead of waiting for everything to assemble here before we go. It also, with CEP, it allows, because of that longer duration, you can actually flatten out your budgets required for all your capabilities at different times. So you can build the systems, say, that are going to go on the CEP, the pre-placement of cargo and habitats. And while it's in transit, you're now using the available budget to build the next set of capabilities you have as well. So we're really, the dream of a big spike in new funding for NASA and we can build all the systems at once is not a reality. And people analyze that quite a bit. But how do you then stretch those out so that you can get all the different capabilities and then you can order them together while still keeping that modularity and flexibility of things changing along the way to get there? I don't know if I completely answered your question, but I can have a discussion on the ARM pieces with you on the side as well. In addition to CEP, there's a lot of other valuable aspects to that of actually moving targets and actually doing deep space operations for the first time on large scale objects that are very valuable to us as well. So. Yeah, absolutely, yeah. Yeah, if the panelists could go ahead and join me up here, and I'll answer one more question, and then we'll move right into the Catalyst panel. Go ahead, sir.
Yeah, hey Jason, Dave Huntsman.
Hey, Dave.
During what was essentially the COTS program graduation ceremony, it was either Administrator Bolden or Gerst who said that headquarters is going to look at what other development efforts could be done by, in a similar way to the COTS paradigm, public funded Space Act agreements, public-private partnerships, et cetera. Where are you guys in that process?
Yeah, so one of the things that we asked about in the RFIs and such that we've been putting out is exactly that. What are some other areas that would benefit from the COTS model? So COTS was highly successful because there was a market much larger than cargo going to the space station. That launch business is way in excess of what just the station model is. So you have to find these unique market cases where there's a government need and requirement, but then also a large enough market demand for it to work as well, to do the exact COTS model. So in some ways, Lunar Catalyst, which we'll talk about here, is a COTS-like model, although no exchange of funds. But you could look at even in the future, should we buy services to land ISRU advancement, ISRU technologies from one of the Catalyst organizations or somebody else that offers that as a service. So we're starting to explore where COTS can and cannot work, but it's not I caution you that it's not you can't use it in all cases just because of that market demand piece. So, okay. So we're going to switch gears.